Welcome. Today we are going to see inhomogeneous initial value problem. In the earlier lecture, we have seen the homogeneous initial value problem. We have stated a couple of theorems also for that. We have also discussed about Hill-Yoshida theorem, which lists necessary and sufficient condition for the operator A to be inverse smooth generator of a C0 semigroup. And that theorem is useful because given the operator, if we can identify the C0 semigroup, we can write down the solution of this equation using the semigroup, and the solution turns out to be TTX. So here, if we do not have just this, but we have some more term on the right hand side, so ddt of psi is equal to a psi plus some another member in the Banach space, or maybe a function of time. Okay, so the Banach space valued function of time. So if you have more data here, then how to find out solution? Okay, so that is the question we are going to address now, and we call that as inhomogeneous initial value problem. Okay, so consider the following inhomogeneous initial value problem. So why do you say inhomogeneous? Because I have some more term here. Okay, earlier I did not have. So earlier it was just f is equal to 0, so the equation was a linear equation, correct? But now it is no more just a linear equation, because here we have some more term here, f of t. But however, it is affine linear in some way, because this is just a constant. It does not depend on the solution psi. So here a d psi dt is equal to a psi t plus f of t, and the solution psi at 0 is equal to small x. So initial point is small x. Small x is a member in the Banach space, and then over time we change. So it looks like just OD, but it's not OD, you understand, because A could be a differential operator, because this for every tie psi t is a member in the Banach space. Okay, so it could be for every t, psi t could be a function of another variable, say variable A. So it is basically a Cauchy problem, it's a PD, where this A, when A is a differential operator, we get a partial differential equation. Okay, so for this problem, we define first what we mean by a classical solution. Okay, so for small t, we consider this problem for time between 0 to say capital T. Here this capital T is different from the semigroup capital T. I'm sorry about using the same symbol both the places, but that is really unambiguous. Why? Because whenever I write down a semigroup, I write down capital T and then in the parenthesis small t. Okay, and if we write down the sometimes we write down capital T as a semigroup also without parenthesis, but then we write down very clearly that let capital T be a semigroup. Okay, so however here this capital T comes, so when nothing is mentioned, then it is just a constant. So this use of the same thing in two different places is really not ambiguous. However, so it needs a careful reading. So for all small t between from closed 0 to open capital T, okay, we study this problem. So where small f is one L1 function, integrable, that means area under the curve if of f is finite. Okay, the mod of f is integrable on 0 to capital T, and we also choose small x from any point in capital X. Okay, so a function psi, which is a function from 0 to capital T, okay, this to x, is called a classical solution of this IIVP, inhomogeneous initial value problem on closed to open T, if the following conditions are true. that psi is continuous on this interval closer to open T. It is differentiable in the interior, so continuously differentiable on 0 to T. Otherwise, I cannot justify the meaning of the left-hand term because we need d psi dt to be well defined classically. And then psi t also should be inside the domain of A, otherwise this thing is not meaningful. Okay, so psi t is in the domain of A for all t in that, I mean, open 0 to capital T. So if I include 0 here, psi of 0 is x, then we are just asking that x also to be in the domain of A, but here x is in the capital X. Okay, so we exclude 0 from here. So psi t is in the domain of A for t positive 0 to capital T. So these are the three conditions. We need also the most important fourth condition, that it satisfies. Okay, psi satisfies this equation. Okay, on this time interval. Okay, if all these things are true, then we call psi as the classical solution of IIVP. Okay, clear. Now we assume that A is infinitesimal generator of a C0 semigroup. It need not be the case, correct? So given any IIVP, that operator which appears on the right hand side need not be, generator of a C0 semigroup, but we are considering the special case where A is an infinitesimal generator, is the infinitesimal generator of a C0 semigroup. And we also consider small x in capital X, and if as before in the integrable, then the function psi, okay, which is defined by the following formula, which would be in the continuous function. So this is defined as psi of t is equal to capital TT of x plus integration 0 to small t capital T t minus s fs ds. Here this integration, so here you can view this as integration over 0 to open t. Okay, so tt minus s fs ds. So this whole thing is a function of small t. It also depends on f. Okay, and then this semigroup is the one which is generated by the operator A. So Tt is the same, A is the infinitesimal generator of the semigroup T. So from that PD with three different information A, F and X, all these things are utilized here, and then we have constructed this psi. This psi is called the mild solution of the IIVP, which I have written it again here. D psi dt is equal to A psi t plus ft, psi 0 is equal to x. Okay, so this function, which is a continuous function. Why is it so? Because ttx is continuous, that we have seen in the beginning of the topic of semigroup. Correct? ttx is continuous in time t, and then if f is L1 function, and this is a C0 semigroup. So here this TTF is L1 log. So this integration 0 to t, this whole integration, this integral would be continuous in t variable, correct? So this is the reason that psi t would be continuous on the closed interval 0 to capital T, the way it is defined here. Okay, so this is called mild solution. Now we have seen for HIVP that if psi t is defined as TT of x, then then that is called mild solution for the homogeneous initial value problem. Here we have additional term f, okay, and then this expression, actually if you put f is equal to 0, then this IIVP becomes HIVP, that is homogeneous initial value problem. Then the mild solution as it is described here also coincides with the mild solution of the HIVP, because this whole term becomes 0. Then if f is equal to 0, the whole term becomes 0, then it also coincides. So it is just a generalization, but that does not necessarily justify why should this be called a mild solution. So in the next slide we are going to answer to this question. So let capital T of T be a C0 semigroup generated by A, and let U be a classical solution to the IIVP. Okay, so assume that IIVP has a classical solution, we call that U, and that IIVP involves operator A, which is information generator of a C0 semigroup capital TT. Okay, so now we construct G function where G of S time S, where S is a point between 0 to T. So G of S is defined to be T minus S US. Okay, for S is equal to 0, U0 is X, and then is T minus 0, so TTX basically. So when S is equal to 0, G0 is equal to TTX. Good. But when S is equal to small t, then it would be UT, because UT and T of T minus T. T of T minus T, that means T of 0. T of 0 is identity, correct? So G of T would be UT, and G of 0 is X, correct? TTX. G of 0 is TTX. Okay, so we understand what is this GS, okay? Then US being in the domain of A, because we have assumed to be a classical solution. So the property of the classical solution is that it should be in the domain of A. So U being in domain of A for each S, so G is differentiable, because since U is in the domain of A, we have seen that the semigroup operated on the point which is the domain of the generator, so that is differentiable. So G is differentiable in the interior, open 0 to T. Okay, so hence we take the derivative. We take derivative here, both sides with respect to the S variable. So dds of gs, okay, dgds is equal to, here I have two terms, tt minus s us. So this term also involves s, this term also involves s. Okay, so first we use the chain rule. Okay, so we take derivative here. So derivative of tt is att, that we know, but here minus sign is there, so we will get minus a tt minus s and us as before. Next we keep the first term as it is, and second term we take differentiate. We differentiate the second term, so plus tt minus s u prime s. Okay, however u solves that IIVP classically. So we know that what is the expression of u prime, because u prime appears on the left hand side, and that is equal to au plus f, which appears on the right hand side. So that we are going to use. So here, as before, this minus a t minus s us appears here, plus tt minus s, and u prime s is written as aus plus fs, and tt minus s operated both the sides. So tt minus s aus plus tt minus s fs. So here I have minus a tt minus s us plus tt minus s aus. Okay, I can interchange between a and t here, because after all u is in the domain of A, so we can do that. And then these two are just negative to each other, so they cancel, and then what we are left with is just tt minus s fs. So here, after obtaining this, we integrate both sides. So when you integrate both sides over the interval 0 to small t, so the left hand side becomes gt minus g0, and right hand side becomes integration 0 to t t minus s fs ds. Okay. So this is of course finite. Why? Because f is in L1 and this is a C0 semi-group. So here we get 0 to t minus all 0 semi-group boundary linear operators. So we get integration 0 to t minus sfs ds exists if if f is in L1. Okay, so this exists, f is in L1. So now here we know ds is equal to tt minus sus, and we have already seen that g of t is just ut and g of 0 is tt of x. So we use that. So g of t is ut, so I write down ut here. G of 0 is tt of x, so I take g of 0 on the right hand side and get tt of x here, and then plus integration 0 to tt capital T of t minus s f of s ds. So we obtain this formula which appears before. So psi t is equal to ttx plus integration 0 to t minus fs ds. Okay. So this is called formula for variations of constants. Formula for variations of constants. And here in this derivation, we have clarified that this formula is actually for the solution, because u was taken to be the classical solution. So if the IIVP has a classical solution and the operator which appears on the right hand side generates a C0 semi-group, then the solution, the classical solution, has this expression. Okay, has this expression. But now if you look at this expression, it clearly appears that this is generalization of the mild solutions that we have introduced for homogeneous initial value problem where small f was 0. And we also recognize that this right hand side is well defined for even if the equation possibly does not have a classical solution, or okay, so like an x need not be in the domain of A. I mean, we can always define tt of x as long as the operator which appears on the right hand side, that A, generates a C0 semi-group. As long as the operator on the right hand side generates a semi-group, we can write down this expression, which is therefore a candidate of the solution. Okay, and therefore we call this as a mild solution. So this proof also clarifies another thing, that for this IIVP, if it has a classical solution, then that is unique, because that necessarily would have this expression, provided that A generates a C0 semi-group. Okay, and that, as I have mentioned, that even if A is not a boundary linear operator, but if it generates, but if there are two different C0 semi-groups T and S having the same influence generator, then both should be identical. So it is unique because A would generate a unique semi-group, and then the classical solution would have this expression. So even if it has, you assume by, then you can prove by contradiction. Even if you assume that IIVP have two different solutions, say U and V, then V of T would also be this. So that would necessarily imply that U and V are the same. So that proves that IIVP has a unique solution. So this discussion gives us various different aspects. The first thing is that IIVP has a unique classical solution. Second thing is that the expression of that in this fashion is well defined even if x is not in the domain of A. So if x is not in the domain of A, it is be a classical solution, because we cannot even assure that this is differentiable. Okay, so surely you can say it's not a classical solution, but still it makes, still one can write down this. So that would be a candidate of the solution, or we can call that as a mild solution. So by this one thing is clear, that we can introduce a more generalized notion of solution of the equation, which is easy to write down. Okay, easy to write down, and we call that as a mild solution. Sometimes we also call that as generalized solution. Okay, sometimes we also call that as generalized solution. And only thing is very important here is that to write down this way is that the operator which appears in the PD in the equation in the Cauchy problem should generate a C0 semigroup. Okay, and that question, that whether it really generates a C0 semigroup or not, can be answered using Hill-Yoshida theorem. Correct? Hill-Yoshida theorem lists down the sufficient conditions under which an operator generates a C0 semigroup. Correct? So we understand now the importance of the Hill-Yoshida theorem, application of that in solving equations. Also, we understand that for two different classes of equation, one is homogeneous initial value problem and there is inhomogeneous initial value problem. For both, we can define the notion of generalized solutions or mild solutions, and we have also written down the expressions of mild solutions. Okay, thank you very much.